Hello my dear students, and welcome back to the chemical kinetics chapter. So students, today we are going to study one of the interesting and important concept called half-life period. Okay, as the title only is indicating you, half-life period means half-life. What is it? See, definition is also simple, like half-life period of a reaction is the time in which half of the reaction is completed, or in other words we can say it is the time period during which half of the reactant is consumed in a reaction. Okay, very simple to understand. Okay, let us consider one example here. See, I have a reactant A and it is giving me the product B. Okay, when the time in the initial state, the concentration of A is 100% and the concentration of B is 0%, means the reaction is not yet started, so the concentration of B is 0 and the concentration of A is 100. Okay, when half of the time, means when the 50% of the reaction is completed, means that time period we call it as half-life period. Okay, so when time becomes half, means half of the total out of 100%, let us say for the completion of this reaction we are taking 10 minutes. Okay, then T half means what? 5 minutes. So in 5 minutes what is happening? Only 50% of the reactant A is remaining and 50% of B is formed now. Now see, the product B formed is 50%. In another words, the concentration of B is equal to how much? Half of the concentration of the reactant. Very simple. Okay, now this half-life period we have to apply it for the different ordered reactions. Okay, so in our syllabus, as we know, we have to study zero ordered reaction and first ordered reaction. Okay, so first let us study about half-life period in zero ordered reaction. Okay, we know that for a zero ordered reaction, what is the integrated rate equation is K is equal to initial concentration minus concentration of the reactant left at time T. Okay, so when T is equal to T half, okay, then R is equal to R naught by 2. Okay, then the substitute these values, what we'll get? K is equal to R naught minus R naught by 2 when the time is half. Okay, then take the T half on this side, so T half-life period of a zero order reaction is equal to R naught upon 2 times the rate constant of that. Okay, so from this equation what we can say, see that for a zero ordered reaction, half-life period is directly proportional to the initial concentration. Okay, so when we plot a graph of half-life period and initial concentration for a zero ordered reaction, we will get a graph like this. Okay, means see, as the initial concentration is high, half-life period of the reaction is also high. When initial concentration is less, half-life time or half-life period will be less for a zero ordered reaction. Okay, now let us move on to the first ordered reaction. Okay students, now let us look into the half-life period for the first ordered reaction. Okay, now we know that the integrated rate equation for the first order reaction, that is K is equal to 2.303 divided by T into log of initial concentration divided by the concentration of the reactant at a time T. Okay, when time is equal to half of the time required for the completion, then concentration of R is equal to half of the initial concentration. So on substituting these values in this first equation, so what we will get? This is what we are getting. This R naught and R naught get cancelled. This 2 goes up. So it will become T half is equal to 2.303 divided by rate constant of first order into log of 2. Now log of 2 value is 0.30. When you multiply this, you will get T half for the first order reaction is equal to 0.693 divided by the rate constant. Okay. So this you have to remember, means you have to remember the half-life period for the zero ordered reaction as well as the first ordered reaction. Okay, in competitive examination many of the questions will be appearing on half-life period only, because it is tricky, and at the same time it will not take much time to solve the questions. Okay, now see, from the equation 1 what we can see, there is no initial concentration term here. There is no initial concentration term. So what we can say that for a first order reaction, half-life period is independent of the initial concentration. What we can represent for a first order reaction, half-life period is independent. This is initial concentration to the power 0. Okay, so it is independent of the initial concentration. Now if we plot the graph of half-life period and initial concentration for first order, then we get a graph like this. Means whatever is the initial concentration, T half will remain the same. You are understanding it? Okay. Next, this is very important, students. This is very important, that for any nth ordered reaction, nth order means it may be zero order, first order, second order, third order. For any nth ordered reaction, half-life period is directly proportional to the A to the power 1 minus n. Or we can say half-life period is inversely proportional to, or directly proportional to 1 upon A to the power n minus 1, where what is n meaning? N is meaning order of the reaction. Okay, now let us understand how does it work, or a shortcut is, see, when zero ordered reaction, n is equal to 0, so A to the power 1 will come. So already we know that half-life period for a zero ordered reaction is directly proportional to the initial concentration. So when order is 0, half-life period is directly proportional to the initial concentration. When n is equal to 1, means when the order of the reaction is 1, then 1 minus 1 is 0. Therefore half-life period for first ordered reaction is independent of the initial concentration. Okay, like that. Now when n is equal to 2, means when the order of the reaction is 2, then it will become 1 minus 2. Okay, then it is A to the power minus 1 will come. That we can write it like how? Like T half is equal to 1 upon A we can write. We can write 1 upon A. So for second ordered reaction, half-life period is inversely proportional to the initial concentration of the reactant. Okay, so here I have written two of the numericals, like how the questions they will be asking in competitive examination. Like here the first question is saying that for a zero ordered reaction, if the initial concentration is doubled, what happens to the half-life period? Now you have to remember that for a zero ordered reaction, half-life period is directly proportional to initial concentration, isn't it? So when this initial concentration is doubled, what happens to half-life? It also gets doubled. Remember this. Okay, next, if they ask you for a first ordered reaction, if the initial concentration is doubled, what happens to half-life period? We know that for a first ordered reaction, half-life period does not depend on the initial concentration. Okay, so this is the graph evident. So if you are doubled the concentration or tripled the concentration, the half-life period will remain the same. So there is no effect on the half-life period of the reaction. Or in other words, we can say for a first ordered reaction, on doubling or tripling or on increasing the concentration of on increasing the initial concentration, half-life period of the first order reaction remains the same. Okay, then next problem, for which ordered reaction half-life period is inversely proportional to the initial concentration? Just now we were discussing here. Okay, you have to remember this shortcut. Then you go on substituting the value of n. Okay, when 0 is there, so it will come as 0 minus 1, A to the power minus 1, it will go above. So this is not that they are asking inversely proportional, means again go on, n is equal to 0, no, it's not the answer. Then n is equal to 1, 1 minus 1, 0, then again this is not what we are recurring. When n is equal to 2, what will happen? So 2 minus 1, it will come 1, A to the power 1 will come, so 1 upon A. Therefore for second ordered reaction, half-life period is inversely proportional to the initial concentration. Okay, like this way they will be asking you the questions. Okay, some more numericals, and we will further we will discuss about half-life period of the first ordered reaction. I mean, what are the type of questions they will be asking and all that we will discuss now. See, you remember this part, students, that is when T is equal to 0, or when the concentration is 100%, T is equal to 0, means initial time is equal to 0. Next, when this becomes a T half, then concentration will be 50%. Okay, next from here, next 50%. Next 50% means, see, when 100 on 0 to 100% is there, when 0 to 100% is there, then what will become here? It will become 2 times half, means it will become 75%. Okay, then what is remaining now? See, when 50% is consumed, 50% is remaining, so half of that means 25%, means 75%. Next, what is remaining now? 25% is remaining, so half of that means it will come 87.5. okay, so sorry, here I will write 87.5% means third half-life. Okay, third half-life. See, here sometimes like this it will go on continuing. Next it will come fourth half-life, means it will come as 93.25 something, or 93.7 something it will come. Okay, so sometimes, see, you have to remember this. In the questions they will ask you what is the time required, okay, for the 75% completion of the reaction. Okay, they will give you half-life period of that reaction. Then how do we calculate? See, it is 2 into half of that is the time required for the 75% of the completion. Okay, that we will see. Or sometimes they will confuse you like this, that is this is half, okay, this is 1/2, then this will become 3/4, then this will become as, or 3/4, this is half, this is 3/4, then it will increase, like it will become 7/8, then it will become like 15/16 portion, like this it will go on increasing. Okay, so they will ask you like what is the time required for 3/4 completion of the reaction, and they will give you half-life period of that. Now remember, it is only for first ordered reaction. They will mention that for a first ordered reaction, what is the time required for 3/4 completion of the reaction. Then you have to remember that for the 3/4 completion of the reaction means 75%, means it will be 75%. So 75% means 2 times the half-life. Now you may ask why it is 2 times the half-life. See, here only, this is your first half-life, 50%. Okay, this is 50%. Now how much of the reactant is remaining? 50% of that remaining. In that 50%, what is again half-life? 25%. So add that 50%, you add 25%, means it will become 75%. See, for the completion of 50%, if it is taking, let us say, 5 minutes, if it is taking 5 minutes, for another half completion, it will take again 5 minutes. So it will be 2 into 5, it will become 10 minutes. Why like this? Because see, whatever the initial concentration, half-life period will remain the same. For the first ordered reaction, whatever may be the initial concentration, half-life period will remain the same. Okay, so it will be 10 minutes. So for the next, that is 7/8, or that is third half-life, what is the time required? It will be 3 into 15. 3 into 5, it will be 15 minutes, like this. They will go on asking you the questions in this way. Okay, or another important concept here, is, when time is equal to 0, what is only initial concentration is there. Okay, initial concentration will be there. Okay, then when t is equal to t half, then a is equal to a naught by 2. It will become a naught by 2. Next, when two half-lives are there, concentration of A is equal to A naught divided by, see, it is already, how we can write it is, see, half of this will come, means 1 by 2, this is A naught means initial concentration I am taking, this is there. So this how can I write? 1 upon 2 square, or it will 1 by 2 multiply by, it will come as 1/4 of A naught. This 1/4 how can I write is, I can write it as A naught divided by 2 to the power 2. Okay, then when t is equal to 3 half-lives, then we can say A is equal to half of A naught divided by 2 square is there, means 4 already is there, means it is square, then it will become as A naught divided by 2 to the power 3. Okay, then we can say for nth half-life, remember this, for nth half-life, what is the concentration of A? A is equal to A naught divided by 2 upon n. Now this is very important, students. On this they will ask you questions as, we'll see the numericals based on. Yes, students, we were discussing the half-life period of the first order reaction, and from this what we can say is that as the half-life period is increasing, okay, we can calculate what is the amount of reactant remaining after nth half-life. Means, say here third half-life, what is the amount of reactant left is initial concentration divided by 2 to the power 3. Okay, so in general what we can say, at nth half-life, amount of reactant left over is A is equal to A naught upon 2 to the power n. What is n? N is the half-life. What is the half-life? Suppose they may give you second half-life or third half-life, like that. Okay, so what is the amount left that you can calculate? Okay, and at this time total time required is equal to n into t half. N is again half-life. Okay, sorry, n is which half-life, means second half-life or third half-life, and the time, this t half means what is the half-life period. Okay, we'll solve a numerical on that. See, here the problem is, for a first ordered reaction, what is the time required to reduce the initial concentration to 1/16th? Okay, they have given half-life period as a 10 minutes. What they are asking you is that if 1/16th of initial concentration is remaining, what they are saying, if 1/16th of the initial concentration is remaining, what is the time consumed if the half-life is 10 minutes? So how can we solve? See, they have already given you that that the concentration of the reactant is 1/16th of the initial concentration, isn't it? So this 16 we have to convert into 2 to the power. Okay, so when we convert it into 2 to the power, it will come 2 to the power 4. So which half-life? It is the fourth half-life. It is what? It is the fourth half-life. At fourth half-life, the concentration of the reactant left is how much? 1/16th of the initial concentration. So what is the total time consumed? So we know that T, total time required, is equal to which nth or which half-life multiplied by the half-life period. Okay, so we have already calculated it is the fourth half-life. So 4 into 10, it is 40 minutes. So what we can say is, in 40 minutes the concentration of the reactant is reduced to 1/16th of the initial concentration. I hope you are understanding. The same question can be reversed. Like how? They will say that for a first ordered reaction, okay, in 40 minutes, for a first ordered reaction, in 40 minutes, what is the amount of reactant left if its half-life is 10 minutes? Okay, they are saying already, now they are giving you T. Okay, you don't know which half-life. They have given half-life period, timing they have given, but which half-life they have not given, but they have given you 40 minutes. Okay, so they are asking what in 40 minutes, what is the amount of reactant left over? So again 40 they have given, so n is equal to 40 divided by what is the half-life? 10. So 40 divided by 10, it will be 4. When you get 4, then we know that this formula you have to apply, n is equal to 4. Okay, so 2 to the power mean 16. So at 40 minutes, the initial concentration of the reactant is now reduced to how much? 1/16. So like this, they will be twisting the questions for you people. Okay, don't forget this thing, very important. Okay, now in general or in competitive examination point of view, okay, they will not always ask you T half. They might ask you any fraction. Okay, so we can calculate now. Time required to reduce the initial concentration to any fraction can be calculated using the formula. Now which formula we will use? See, T1 upon N is equal to 2.303 divided by K into log of 1 divided by 1 minus 1 upon N, where N represent any fraction. For example, okay, when T is equal to 1 upon 3, 1/3 you have calculated 1/2, now we have to calculate 1/3. Then what is the equation? So T1 upon 3, time required for the 1/3 completion of the initial concentration, is equal to 2.303 divided by K log of 1 divided by 1 upon 1 minus 3. So what you will get now? This you will get it as 2.303 K log of this. It will come as 3 goes this side, so 2 by 3 you will get it as, 2 by 3, or indirect it will become 3 by 2. It will become 3 by 2. So they will ask you such questions. Means in competitive examination, they will give you 4 different formula, and they will ask you time required for the 1/3 completion. Then this is the formula that you have to make use of. Similarly, they can ask you 3/4. They can ask you 3/4. Then what you have to do? Same formula here, 1 upon 1 minus 3 by 4 you have to use. Okay, so it will become, I guess, 4 upon 4 by 1, so log of 4 it will become. Okay, like that you can go on calculating. So any fraction, and this is all what we have discussed. It is only for first order. Remember this is whatever now so far we have discussed, it is only for first order reaction. Remember. Now one more thing is there that we have to discuss is, okay, that disintegration of radioactive elements. See, disintegration means in gaseous we say, as we say that gaseous reaction, decomposing. Okay, like nitrogen pentoxide decompose means it will break into. So now disintegration of radioactive elements, okay, means a radioactive element like radium will be disintegrating. It will be radiations it will be emitting. That emitting of radiation, okay, when element is radioactive and it is emitting radiation, means the amount of that element is decreasing. That we call it as disintegration. Okay, so even the disintegration of radioactive elements follows first order. Okay, I'll say disintegration of radioactive elements follows first order. Okay, then we can say lambda is equal to 2.303 divided by t into log of n naught divided by n. Okay, let us see what is lambda. Lambda is called as disintegration constant. Disintegration constant. Like in for normal reaction you have got rate constant. For radioactive element we call it as disintegration constant. Then n naught is equal to number of atoms when time is 0, and n is equal to number of atoms at time t, at a time t. Okay, so this is for disintegration of radioactive elements. Then half-life period, it will be like, we will write lambda is equal to 0.693 divided by t half. This we can write it as t half is equal to 0.693 divided by lambda. So from here you can say that half-life period and disintegration constant are inversely proportional. Therefore t half is inversely proportional to disintegration constant. So in competitive examination they will be asking this, I have seen it, that if the disintegration constant value is high, then half-life period will be less. Half-life period will be less, means they will give you the disintegration constant for 2 or 3 elements and they will ask you which element will disintegrate fast. Remember this. Now half-life period and disintegration constant are inversely proportional, means what? I'll write lambda value is less. Lambda value is less. If this value is less, this value is more, means half-life time is more. Okay, so lambda value is less, then the element is highly unstable and disintegrates quickly. Okay, so for an element, if the disintegration constant value is more, then this will be if less, so if this value is more, t half will be less, means quickly the element will be disintegrating. If this value is less, then this value will be more. When the half-life time is more, the element will remain for longer time. So these are the questions which will be asked on radioactive elements, and even for any fraction of the reactant remaining after say any fraction of the reactant remaining at time they will ask, then how to calculate that? This is by using this formula you can calculate. Okay, so this is about the half-life period of the first order and zero order also we have discussed. Okay, so in the next class we will discuss about the collision theory. Okay, thank you students.